Alright, let's give this a go. Hey everyone, how's it going? Sorry about the problems this morning. There we go. Alright, let me know if you can see my screen. Let me know if you can hear me. Let me know if it's all good. Thanks for letting me know about the microphone. I don't know. I upgraded NixOS a while ago. I think it was last week I upgraded NixOS. And I enabled OBS without Pulse Audio support by accident. And then for some reason Pulse Audio couldn't find my microphone until I rebooted. So I don't know what's going on. But it's all good now. Real good. Cool. Awesome. Thanks for letting me know. Great. So, last week we worked on state and state T in the FP course. This week we're going to work on, well, we've already done the parser, so we're going to work on MoreParser and Json Parser. And Json Parser is actually going to be a fairly complete Json Parser. It's actually going to be pretty true to this specification here. There's a lot of things here that are unspecified in this JSON spec, this particular one here. But I think we hit pretty much everything that is specified. So that'll be the goal. Make a JSON parser that's pretty much to spec. Cool. But first we have to do MoreParser. So let's open up moreparser.hs. I'm going to go over to I'm going to open up GHCI over here. Load everything up. Cool. Alright, let's have a go at this. So the first thing here is parses the given input and returns the result. The remaining input is ignored. So remember that a parser, let's go back to parse because we haven't done parser in a while. So parser's got a few things to find. It's got this parse result thing, which has got like a heap of different type of errors that you can have when you're parsing. It also has an input, which is just a list of characters. So it's kind of like our string type. And then we get down to parser. So parser is the way to read this. So we can actually change this to a new type even, but we're just using data. Remember that a new type is just a data thing with only one constructor. So we've got a data type here, and it's got one constructor P. So the data type is parser, has one constructor P. And to construct a parser with the P constructor, you have to supply it a function from input to parse result A. So remember, input is like our string, so it's kind of like it's string to some sort of error type or a successful parse result. So either we've got something that's succeeded, or we've got an error based on this string that you pass in. And you know, the data type is parameterized on this A thing. So you can make a parser of int, you can make a parser of boolean, you can make a parser of double, anything you want, you can make a parser for. I think at the bottom of this we wrote a parser for person. Yeah, here we go, person. So you can make a parser for a person. And what we did with that is just combine together heaps of different things together to make a person. So that's the idea behind a parser. So if we've got a parser and we've got an input, so we've got a string, then we can get back an optional A. So you can see the implementation here. All it does is it runs the parser, so it extracts out the function, runs it, and then just checks if it's a successful result. Otherwise, if it's some sort of error, then we just give empty. So we don't care what type of error it is. Just that it's an error, then we put that to empty. So that is this bracket dot bracket function, just a way to run a parser. Cool, so the first exercise here, first exercise in MoreParser is write a parser that will parse 0 or more spaces. So something that will just parse 0 or more spaces. And notice how it gives back the spaces that it parses. So if we go to parser, let's browse parser. That'll be useful. So if we browse parser, or course.parser, there's a lot of functions we wrote last time. Will I publish a recording of this anyway? Yes, I've been uploading these all to YouTube. If you just go to YouTube, type in there we go. Just type in Brian McKenna FP course into YouTube. It'll come up a playlist that I've got and a heap of videos, so you can go through these. This is the playlist that I'll be adding to. So there's already 6 videos in there, and I'll add this one to that. So if we go through course.parser, we'll see a heap of different functions. One thing that we should do is if we look up info for chars, because we need to give back a chars, right? We need to give back this chars thing. You can see it's just a list of characters, just a list. So what we want to do is get back some sort of function that'll just keep taking spaces and produce a list from it. And if you look at list here, it takes a parser and it produces a list of parser. Oh, thanks for subscribing to me. So take a list. So if we come down here, what I want to do is say list, and if we look at what else we've got in here, we've also got space. So we can actually probably just say list of space. Let's see if this works, and it does. Let's make sure it does the right thing. And it does. It just keeps parsing the list of spaces. Cool. Let's make sure it works with 2 spaces and 3. Yep, it's all good. Cool. So list of space. I mean, you can kind of tell. Write a parser that will parse 0 or more spaces. If you give it back a list of spaces, then you're all good. Cool. So now we need to write a function that applies a given parser, then parses 0 or more spaces, then produces the result of the original parser. So it will, if you look at the example down here, if we say token is a, so is, if we remember is, takes a character and then produces a character, a parser for that character. So you can say is, I don't know, t, and that will just mean that it will only parse the t character. So if I say parse, you can see that it works there, but if I say that, it will say unexpected character. So is will just parse the one character a, but notice how there's a space after the a in this example, and the result gets rid of the space. So there's no space in the in like the rest of the string, and there's no space in the character that it returned back. It just got rid of the space. So that's what we need to do, make a parser that will get rid of the space. So it needs to parse what we give it. So we've got this parser here, so I'm going to call that P. And it needs to run that parser, but then it also needs to run the spaces parser, but give back the first result. So let's write like this. Let's start off with lift2. We want to write some sort of function. I'm going to put a hole in here. I'm going to say run this parser, but also run the spaces parser, the one that we wrote just above, which just creates a list of spaces. So I'm just going to say lift2. Remember, lift2 has this type. So if we give it a parser of the character, actually no, this is a parser of a. So we give it the parser of a, and then we give it the spaces parser. We're going to have to combine together those 2 results to get a parser of a in the end. So we've got actually, if I just reload this, it will tell me exactly what we need to do. So to do has got this whole a and a characters and an a. So this is the result of parsing the first one. This is the result of parsing the spaces, and that is a result that we have to return back. If you look at this type, you might be able to see it looks very similar to a function that we've talked about quite a bit before. This is the const function. So if you look at const a, b, a. So it just, if you give it const 1, 2, you get back 1. So it always gives you back the first thing. And that's what we want to do in this case. We only want to return back the first thing here. We only want to return back what the parser parses. We don't want to use whatever the spaces parses. So we don't care about the spaces, we only care about what P has. So we can write it like this. And I think this should work. So that works. And that works. Notice how this space here, it comes into this const function. The space comes into the const function, but then it just disappears. It's not used. Only this a is used. So there we go. That's one way to do it. Now there's actually a function for doing this. This is so common that there's actually a function for doing this, and it is this one. So we call this like I call it usually write apply. I don't know if the FP course calls it something else. If we look in applicative, we implemented this function and we called it apply left apply. Okay, this one's left apply. Yes, sorry, this is obviously left apply. the arrow is pointing to the left, it's the left apply. So we implement this function, and all it does is well, actually, if you look at the implementation, it's lift to const, so it's exactly what we wrote before. It's just so common that we actually have a function for it. Cool. So that's the token parser. It'll parse something and then just drop whatever spaces come after it. Really useful function, that one. What we could even do is drop that. Whenever you see an operator like this, you can actually just rewrite it into a point free version like that. So that's exactly equivalent. It's just apply that function. Sorry, apply a left apply with spaces. Cool. Next one is chartoke. Write a function that parses a given character followed by 0 or more spaces. Here we go, there's a tip here. Use toke and is. Okay, well, we've got the character here. So we need to use toke. Isn't that exactly what we want? It is. The tip was maybe a little bit too straightforward there. We can even change this to a point free version like that. So chartoke is just an is toke. Write a parser that passes a comma followed by 0 or more spaces. I think this is just chartoke comma. Sorry, I'm doing this one's pretty quick because I can see what it is. Oh, here, the tip even says use chartoke. There we go. And the reason why these ones are so small, like these aren't really meant to be exercises to kind of really test you. These are more exercises to build up to building something bigger. So we're going to use these functions, just like how we in parser we wrote like a first name parser or in a surname parser and so on. We used all of those things, and they weren't that complicated, but we used them all in a way to build like a big person parser. And we're going to do the same thing here. We're building up to make a Json parser. So write a parser that parses a comma followed by 0 more spaces. That should be that. I guess let's run our test. Yes, true. Cool. And this one should succeed. Yes. Cool. All good. Now write a parser that parses either a double quote or a single quote. So we're going to have two different possibilities here. Use is and or. So if anyone remembers this or thing, it will try one parser and then it'll try the other one. So we can say is either a double quote or is a single quote. There we go. And that compiles, so I think that's good too. So that's either a double quote or a single quote. Write a function that passes a given string. Fails otherwise. Use is and traverse. So we're going to get given a list of characters. We need to make a parser of characters. So we need to make sure it is. So for the first character, we need to make sure that parses. Which is this system? I don't know what you mean by system. I'm working in a language called Haskell. It's a programming language called Haskell. It stays true to the idea of mathematics and functions. The system that I'm using, the operating system, is NixOS, which is a purely functional operating system as well. As you can tell, I really like functions, and so I use functions everywhere. Write a function that passes a given string of fails, otherwise use is and traverse. So what we want to do is for every one of these things, remember that this string is actually just a list of characters. So for every character in this list, we want to run is, right? We want to say it is A, then it is B, then it is C. That's what it means. I'm extremely happy with NixOS. I use NixOS for absolutely everything. I've got two computers right here that are running Nix right now. I've got a personal computer that I use as well that runs Nix. I've got a media center that runs Nix. Like everything, my router even has things built from Nix. I've got these little computers around here running Nix. Yeah, I use Nix for absolutely everything. At work, we use Nix as well. So yes, I'm completely sold. Yeah, so this is the computer I'm running at the moment. Dell Precision M3800. For Marketplace, which is a product I work on at Atlassian. This is all deployed using Docker images, but the Docker images are also built using Nix. So yes, Nix I use for work and for home, and I highly recommend it. It's extremely good. You remember your try of NixOS? Yeah, it's you really have to know what you're doing to use NixOS. It's not something that you can kind of just jump into and learn as you go. It's something that you really have to invest time into. That's kind of the downside of using Nix. So we've got a hint here, use traverse and is, because what we want to do is use is. If you traverse with that, it'll run is on the first thing, run is on the second thing, run is on the third thing. So traverse is, I think, is the implementation here, and it is. So just go through the list and say each one is the character that it wants to be. Cool. Write a function that parses the given string followed by 0 more spaces. So this looks exactly like what we had before, which was okay. So it says here use toke and string. So this is just toke.string. Because before we had chartoke. And remember, chartoke was the implementation of chartoke was toke.is. So this is very similar, but now it's, I think, toke.string. There we go. That compiles. Okay, now write a function that tries a given parser, otherwise succeeds by producing the given value. Okay, so it's either going to try and parse something, but if it fails, it's going to give back the given value. So what we can do is say we've got the A and P. So A is the default value that we want to give back if this parser fails. So what we want to do is run the parser, but if it fails, which is the OR, then we want to give back A. So I'm going to say pure A. This is going to construct a parser from the A, which will always succeed. So it's going to try P, then it's going to try this parser, and this is always going to succeed. So I should be able to say option, let's run the examples up here. Whoops, I'm getting a phone call, hang on. Sorry everyone. Alright, where were we? Sorry, I'm on call at the moment, so always have to check my phone, but I should have known that it wasn't actually, it was someone else in a way. I should have known. Because I usually have a like doomsday ringtone for my on-call calls. Okay, so write a function that, okay, we did this, so the option parser. Oh, that's right, we're going to test this out, weren't we? And we just did. Okay, cool, that's all good. And if we fail, then we get back the X. Awesome, cool. So we got the option parser working. I don't know about doom. It's a spooky, I guess, ringtone, just so that I know that it's on call, that something's down. Okay, write a parser that parses one or more digits. So list one and digit. I think they've given us a solution here. List one digit. I'm just thinking digit looks like, yeah, it's a parser of character, and list one will, parse one or more. So there you go, list one digit. Cool, write a function that parses one of the characters in the given string. Use satisfy and lm. Okay, so if we remember satisfy, it takes a function from character to boolean and then produces a parser of character. So we have like a predicate that we can supply here. So we can say satisfy. I think what is just this. So we can satisfy equals to a. So then we can say we can just give it a boolean expression. And it says here use lm. Use lm. So let's look at lm. So lm will say if we've given some sort of value, it'll check if that value is in the list. So we can say lm1 is in the list of 1, 2, 3. But in our case, we're working with, instead of these numbers, we're working with characters. So I can say is a part of A, B, C. So there you go. That's the lm function. So what we can say is, what do we want? We want satisfy. We get our character in here. And we need to return a boolean, right? We need to return a boolean. Oh, whoops. So we've got our characters here. So our characters. So I need to say is C, an lm of C's. There we go. So that is an implementation for one of. So I can say one of there we go. So if the first character here is one of A, B, or C, and that succeeded with that. So if I change this to D, failed. Cool. And I'm actually getting a warning here, or okay, so it says here I can use infix of elem here, so I don't know why it's suggesting that, but it says it likes that a little bit nicer. And then it says here what we can do is avoid the lambda, so we can actually delete that. So there you go, that's hlint, that's telling me these different refactorings. So we can do that. To satisfy backtick elem cs. So remember the backticks is a way of changing any sort of identifier into an infix operator. So remember that operators can be put in prefix by putting them in parentheses. So these are the same thing. Usually identifiers are prefix, so if I put p here, but what we can do is put them in backticks and then we flip that, so then it turns into infix. So we've got a way of turning identifiers, just alphanumeric identifiers, into operators, and then we've got a way of turning operators into just identifiers using prefix notation. So you can kind of go backwards and forwards between the two, which is really useful. That's what we're doing up here with elem. We're just saying elem, make it into an operator, and then we're just putting that at the beginning. So this is actually the same as doing flip as well, same thing. But we'll trust hlint and we'll do whatever hlint says. So now this one is none of. And this one says use satisfy and not elem. So I think we can guess the implementation of this. It's going to be exactly the same as what we wrote before, except we're going to use not elem this time. I don't think we even have to test that. I think we know that one's right. Okay, now write a function that applies the first parser, runs the third parser, keeping the result, then runs the second parser and produces the obtained result. Okay, that's confusing. Let's look at the type. Parser of O, parser of C, parser of A, and then we get back a parser of A. Okay, so it's going to parse this one first. Hang on, which one is it going to do? Yes, so it's going to do this one, then that one, and return back the result of the second one. So even though this, so this is like beginning, end, middle, and we get back the middle. So we're going to say it's between two different parsers. So begin, end, I don't know, P. So what are we going to do? So it wants to use the monad instance. I am not going to do that. So what I know is that with the applicative, you've seen that I used lift2 before. And I said run, so we're given a function, run one parser, which was, what was it? It was P and then spaces. So I had that, something like that before. And this is a way of doing, what do you do? Sequencing different parsers. So we can run one parser, then we can run a second parser. That's what lift2 does. So what we're going to do is do lift3. Yeah, this is coding exercises. So these are parts of the Data61 FP course. So this is the functional programming course. I'm just going through, I've been teaching this functional programming course at work. I've been teaching people functional programming at work. I'm actually, I've been teaching a lot of my co-workers how to do functional programming using this. So we've already gone through a lot of these. We've gone through list, functor, applicative, monad, state t, traversable, and parser even. So we're going through just these two exercises. So this is really far into the course. So if you're watching this without watching the previous ones, please go watch my YouTube videos. We go really basic stuff like just how I guess functions work, then how lists work, and so on. This is getting pretty advanced, so that's why I'm going through these pretty quickly, and I'm not giving too much detail. Also because these are building up to something a little bit more interesting. Yeah, so to be able to implement parser, you actually need to know applicative. So I'd go back and watch the applicative exercise, whichever one that is. I think that might be video 2. Yeah. But yes, I'm working through these not to show hey, I can do these exercises. I mean, to me, I've done them so many times before. This is not as quickly as I did them the first time I did them. This is probably the 4th time I've done these particular sets of exercises, and so I'm just showing everyone how I teach it, and how I derive these results, and how you can get to like a mechanical derivation of some of these results. Cool. So lift2 is a function that we used before. There's lift3, which is saying I want to run one parser, then another parser, then another parser. Then I've got this function to combine the results. So if I come over here, I've put a hole in here. So this is underscore to do. If I put a hole in, go up to the thing here, it says here, now I've got this function to combine the results of running each of these parsers. So this is going to be the parser that ran first, one that ran second, one that ran third. Then we have to give it back a result to make this new parser that we're combining together. So we're going to run 3 different parsers, then we're going to make a new parser that runs those 3 and gives back some sort of result. And you can see here we've got the O, we've got an A, and we've got a C, but we want to get back an A. So if you combine these results, there's only one thing you can really do here, which is return this second one. So let's write that out. So we're going to ignore the O, get out the A, ignore the C, give back the A. Okay, anyone want to guess how to refactor this? I can see here if we drop this part, I can say const. And then what's this say? Okay, there you go. It says use const here because it's found underscore to const. So why don't you use, perhaps you want const. So there we go. Thank you, HLin. So lift3 with const of begin p end. So if we run this, what we should see now is that we can pass between 2 different things. So we can say the beginning is a left bracket, the end is a right bracket, and there's going to be some sort of character in the middle. And there you go, it's parsed it out. And you can see there's nothing in the result left, so it completely consumes these inputs. Cool. So write a function that applies the given parser in between the 2 given characters. Okay, so this pattern up here, see how we do begin between is and then is. So we're constructing 2 parsers here. We're saying is to construct a parser, and then we're using is again to construct another parser. This one, we don't have to do that. It just says, you know, use is for us. So it should be able to do between is. I think that's what we want. There we go. HLin wants to turn my code into SKI. That's the best way to write code. Yes. Seen Haskell in the past and didn't understand some of its designs. Yeah, it's it's very different to pretty much every other language that you would find. So yes, it takes a long time to understand a lot of its design. It takes a long time. It's a big investment. I think it's completely worth it. I really do recommend going through this FB course and getting used to functional programming. It's really good. Okay, so write a function that passes 4 hex digits and return the character value. Return the character value of the hex digits, right? So we need to read in 4 hex digits and return the character value of that. Okay, so let's look at this read hex thing. Read hex takes in characters and returns an optional. So read hex. Okay, so this thing just keeps reading in hex digits and creates a optional of A. So it creates some sort of number for us. Okay, and what do we want to do? We want to parse 4 hex digits and return. So is hex digit. Okay, so we want to do is hex digit. And it says use let's say use satisfy with that. So I'm just guessing, I'm just combining together the things. So we've got this is hex digit, and we've got this satisfy thing. So notice how satisfy goes character to bool. That's what is hex digit is. So let's chuck that in there. I'm just plugging things together. So now we've got a parser of character. Then it says use replicate A. So looking at replicate A, takes an int and something and produces a list of something. So if I say replicate, I'm just guessing because it uses 4, right? 4 hex digits, and so it wants an int here. So let's just chuck that in, 4. So there we go. We've got something now that will parse out characters. So let's parse. There we go. So notice how it's returned the result here. So A, B, C, D. If I go E, it's not going to consume the E because it's only doing 4 of them. And if I only give it 3, then it'll say end of stream because it wanted 4. So it's always going to parse 4 hex digits, which is exactly what we want. So at the moment we're getting 4 hex digits in, but notice how we're not returning the character value of those digits. It's always just going to give us back the actual string. So that's where I think we want to use read hex. So if I was to map, so remember fmap, if I was able to map these, if I was able to map the hex digit that gets the big hex string that comes in, if I'm able to map it with read hex, then we get back this thing. Okay, so we're getting somewhere. So let's use, what is it? Let's copy and paste that code in. So we've copied and pasted that in. So we're creating a string that's got 4 hex digits in it. Then we're going to, we want to use this read hex function, but notice how it gives back this full thing. It gives back a full. But we want it to be an error if we don't want this full in there. We want it to actually be the character result. So instead of this number, we want it to be a character. And instead of this full, we want it to be a result. So what are we going to do here? We need to, I think we need to do this, I think. So we need to use this bind. So we need to say, we need to use bind, because what we want to do is take the list of characters. So we want to take the characters out, parse them, and then create a new parser based on that. So instead of having this full and empty, we want to have it construct a new parser, because we want to have the empty go to an error, and we want the full to go to a successful parser. Okay, so I think we're going in the right direction there. Is there any compiler that adds more features than the main one? Any compiler that adds more features than the main one? Well, GHC's got a lot of different features. So there's GHC extensions. And this is a massive list. If you look at this, it's a massive, massive list. So there's a lot of features in the main GHC Haskell compiler. So there's all of these, a lot of different features that you can extend. So these aren't enabled by default. Well, some of them, I think some of these are enabled by default, but not all of them. So you can enable these and kind of make your own kind of part, I guess like extended Haskell. So you can enable some of these and make an extended version of Haskell. There are other compilers though, like I work on this thing called Edalang sometimes, which is Haskell on the JVM. So this adds the feature of running on the JVM to Haskell. This is really good. Highly recommend looking at Eda. It's really well made. Yeah. Hey Oblivioner, how's it going? Why the Chinese in the bio? I think I've got Korean in there. I don't know if I've got Chinese. I'm trying to learn. Well, I was trying to learn Korean and well, I was trying to learn a little bit of Mandarin, but that didn't really work out very well. It's a hard language. Okay, so what they wanted is this list of character to a parser of characters. So I'm just going to introduce a lambda because that is the constructor for that. Whoops. Did I... Do I need parentheses here? I might need parentheses there. Yeah, I do. Because I know I need to get back a parser of character. So I'm going to read, was it read hex? I'm going to drop this let, I'm going to just put it over here. Okay, so we need to give back a parser of character. What do we have in scope? Well, we have this H, so an optional of A. An optional of A. So what do we want to do with the optional of A? We want to So I'm using, is this optional thing exist? So I'm looking at optional, whoops, let me comment this out. So the type of optional, oh, there we go, I had the things flipped. So I want to convert this optional into a parser. That's what really the goal here. Okay, am I getting closer? No, I'm not. Oh, because it needs to be parser result. Ah, that's right. Okay, so pure. I want pure there. So I'm saying take the full of, you know, reading the hex, take the full, turn it into a parser by doing pure. I think that's what we want, is it? And then no instance of numchar though. So we have to say, what is that? Oh, this is getting annoying. So I want to say from integral, I guess. Can I do that for a char? I can I? No. How do you convert a? I've forgotten the function to convert a int to char into digit. No, that's not what I want. I've forgotten this function. We could do that. Would this work? I don't know if that's going to actually do the right thing, but we'll see. When you're reading about your source stuff like sized integers, sized floats, subranges, searching for stuff like sized integers, sized floats, subranges, it is possible to do that sort of stuff, but like I was saying with the extensions, you'll need to enable some of these to be able to get you know, sized. I mean, there are sized integers. Like I use a lot of data.word a lot. If you look at some of my other streams, I've been implementing Sonic the Hedgehog in Haskell and you know, word 8. So this is an 8-bit unsigned integer type and things like that. So we do have sized types, but GC's only got so many built in. So we've got word 8 up to word 64. So like if you wanted a word 128, you'd have to make it yourself. And it wouldn't really have like any hardware support. You'd have to either extend GHC to do that, or you'd have to write some sort of macros or something like that. Do I contribute anything cool to Cardano? No, I have not. Especially since, there is, if you've Googled my name, it might come up this. Especially since IOHK does a lot of Haskell, it might come up this website. If you look at the team, you might see a Brian McKenna in here. That's not me. So I don't know if you're looking at the people that make Cardano. These people work on Cardano, and there's a Brian McKenna that works there, and that's not me. And they write Haskell, but that's a different Brian McKenna. I am interested in Cardano though, but I haven't really contributed anything to it. I do think Cardano is pretty cool because it uses Nix and Haskell. I'm really interested in more of the implementation. I think they're doing a good job there. Is char what I want? Let's look at char. That char is probably what I want. Oh, there we go, CHR. There we go, that's what I want. Thank you so much, CHR. Okay, so then we've got to make a parser that fails. Thank you. Thanks for pointing that out, Pedro. Cool. And now we need to make just one that fails. Yeah, CHR is just because it's in it's defined in oh, there you go. It's in jc.char. It's in, if you look at the core, it's in the core exports here. So the cores.core exports CHR. Anyway. Okay, so now we need to make an unexpected, I guess unexpected string, would that be it? Unexpected string. Yeah, here we go, failed. So we say failed with unexpected string of, what's our string? C's. Cool, let's give this a go. Okay, it's compiling. And I think I can actually drop this H because it's only used in one place. It is. So this one was pretty complicated here. And yep, that's what we want. Cool. So what we do is we get the 4 hex digits. Then using those hex digits, we come in here and we read off, we read them into hex. We've got this existing function which will read like read a string into some sort of integer. That integer then is converted over to character if it's success. So if it's full of some sort of integer, then we just convert it into a parser. Otherwise, it failed, and we can give back an unexpected string. Cool. So let's go parse. Okay, DLE, is that what it said? DLE, that's cool. Let's run this one. 2591, that's right, and error with hex 001, that's good, and error with that. Oh, good. I am puffing fresh on GitHub, and I thought Cardano SL, I guess I made up. I mean, I did try and run Cardano's wallet and stuff a while ago, so I probably did something with it. Actually, I think I was running the server, and so I needed to, yeah, I forked it because there was some sort of thing in there that I needed to change to run it. Have proper error handling in the course now. Yes. Yeah, it's good. Yes. Yeah, there was before it was a little bit dodgy, wasn't it? I do remember that. Cool. So hex is all working finally. So now we need to make a function called hexu, which will just parse the character u followed by 4 hex digits and return the character value. So it's exactly the same as before, except it has a u at the beginning. I think we can do that with is u, and then we're going to say hex. So we want a u, and then we want anything hex. We only care about the hex. We don't care that there's a u at the beginning. We only care, well, we care that there is a u at the beginning. We don't care the result of u being at the beginning. So therefore we can ignore it. So this is right apply, which just ignore everything on the left hand side. So we're ignoring this u. We're just saying that it needs to be there. Write a function produces a non-empty list of values coming off the given parser, which must succeed at least once. Separated by the second given parser. Okay, so it's going to be separated. We're going to parse a lot of things, but separated by the second parser. So we've got this parser here, and we've got the separator. And we need to parse it at least once, and then it needs to be separated. Alright, this one's going to be interesting. Okay, so use list and the monad instance. So I'm going to say, what can we do? So we want to use list. So I'm going to say s. So we don't care what the separator is. We don't actually use the separator. So notice how we've got a parser of s, and we don't have s in the output here. We don't actually care what the s is. And we don't care about this parser. We only care that it exists and that it does parse a result. We don't care what the return type of this parser is though. So this will do something. It's not going to give us the right thing though, because if we say, it will parse this though. So I can say A. And so notice how it's parsed out each A. So as long as it starts, so the only problem here is that it hasn't, needs to start with an A. So we need to also add in an A at the beginning here. So I'm going to say lift 2. So we're going to sequence things, right? We're going to sequence our parser P, and then we're going to say list. So we're going to parse out 1, and then we're going to parse out our separator, and then another one, and then our separator, and another one, and our separator, and another one. Okay, and then we've got to do. We need to do this, and if you look at this a little bit, you might recognize a function here, a list of A to a list of A. What can we do here? We can either take this second one, but that's not quite what we want because we actually want to use this A here. We want to return that in the results. This looks like something. It looks like something in list. This exact type. There's something that actually has that exact type, and it is cons. what we're doing is saying parse out one, then parse out a list of them, and then just put this one on the beginning. Cons it on. Will this be a series? Yes, it already is a series. So this is part 5, I think. I think 6 here. Yeah, there's only a 5-minute one in there. So I think this is part 6. So this is the Data61 FP course that I've been going through. So you should have a look at this this playlist on YouTube. It is a series. This is actually quite far into the series. So if you're watching this, if this is the first one that you're watching, you probably won't get a huge amount out of it. You probably should go back and watch some of the other videos. Cool. So you can see is set by one is working here. So you've got A, B, and C separated by this comma. And the way it works is it's just parse out one, cons it onto a list of parsing out all the separators. So now we're going to write a function set by, which will use set by one. So notice how the tip here says use set by one and or. So we should be able to say set by one or pure nil. So if anyone remembers our implementations of list and list1, we had something very similar to this. And so what I'm saying here is use set by one, so try and parse out one, but if it fails, if we're not able to parse out one of them, then well, nil. So what we want to do is make it so that this so this always succeeds with an empty list if it can't parse anything. So you can see here it can't parse a character and then a comma, but we still get back an empty list here. So it doesn't matter, so in this case it actually succeeded, right? So it did parse out one, and if we try again with a comma, it will succeed, but it'll always succeed. That's kind of the point of this function here. It'll always succeed. Cool. So set by is exactly like set by one, except it always succeeds. If set by one were to fail, then it just uses returns an empty list. Write a parser that asserts that there is no remaining input. Okay, how do we do this one? So there's no remaining input. I wonder how we do this. So I'm going to construct my own parser then, because that's the only way I'm thinking about doing this. So we've got a parser of characters. So remember to construct a parser. So the type of P to construct a parser. So this is constructing a parser. We have to give it a function from input to parse result. So I'm going to say input is our C's. And then we have to give it a parse result. So if I look at the whole here, we need to give it back a parse result of unit. What we have in scope is our input. So what I'm going to say is if C's is empty, then we're good. So that's going to be a result of unit. Otherwise, what do we need to do? What's a good error result for this? Expected end of file. There we go. Cool. There actually is an error type here. So say failed, is it? Failed expected end of file when we got C's instead. Okay. Oh, don't need the failed. Failed constructs a parser for us, which we don't want. Okay. Oh, and we need to give it back the rest. So result of C's, is it? There we go, getting closer, and my null is not right. Is there is empty? There we go, is empty is what we wanted instead of null. Null is the standard library, Haskell standard library version of it, so it's in memory. Cool. So we construct a parser, take the input. If the input is empty, that's good. Then we get a result of unit. Otherwise, if it was not empty, so that means that we haven't reached the end of file, then we say we expected the end of file, but we got C's. Is NixOS Package Manager something similar as FreeBSD jails? Not really. When you do a build, you can actually build it inside of a jail. So there's a few different layers to Nix. So there's the Nix language or expression. There's a Nix expression language, which is basically a programming language. On top of that, you've got the Nix package manager, and then on top of that, they build something called Nix OS. So the package manager has the feature of evaluating this purely functional language, the Nix expression language, which creates a description of a build. Then it executes the builds in a way that it hashes all of its inputs and produces an output. So it produces an output based on, like, it basically hashes all of its dependencies, creates like a hash that puts it into the Nix store. So then you kind of got like a deterministic way of referencing something. So if you were to build Hello World, for example, that would depend on like GCC, for example. So it would take the hash of the version of GCC you're using, create a hash based on all of its dependencies and even the source code of Hello World, create a big hash, and then say, this is the output I'm going to produce based on all of these inputs. And so Hello World will put out, this big hash, and that's where Hello World goes. And so everything in Nix goes into this big Nix store. So I can actually like list my Nix store, which is massive Nix store. So all of my applications go in this massive amount of libraries, all go under this /Nix/store. So everything gets hashed and puts it into there. Sound like blockchain sort of a package manager? Yeah, it's all like what would you call it? I wouldn't say it's content addressable, but it's almost content addressable. So the content is the dependencies that it has rather than the actual output, if that makes some sense. So it's like the constraints here, this hash actually comes from the dependencies of constraints rather than on the actual output that constraints is going to generate, if that makes some sense. Actually, no, because this one's a tar, that's actually a bit different. That one actually is content addressable, but there's some things in here like this. This hash comes from the dependencies of XZ, it doesn't come from the output of XZ. But the output goes into this directory because this is the hash of its dependencies. So it's just a way of having like deterministic hashing and then referencing things. And so it's purely functional in the way that everything has to be referenced explicitly. Hey Grey Fox, how long have I been studying programming? I've been programming professionally since, like full-time professionally since 2010, I think it was. 2010, maybe 2011. What's the difference between hash and crypto? There's such a thing as a cryptographic hash, so there's not really a difference. Sorry, I can't really answer that question. It's not really well formed, I guess. A hash is just a way of taking some sort of input to some sort of smaller output. So write-a-parser produces a character and satisfies all the given predicates. Use sequence and list and. Okay, wow. Okay, so we're going to have a list of predicates. So instead of having just one predicate, remember how satisfy was character to bool, and then we create a parser character. This one's going to have a list of predicates. So we're going to have to satisfy all of them. All right, use sequence and list and. Interesting. How are we going to use sequence in this? Let's have a go. So we're going to have a list of predicates, so that's our predicates. Okay. Then it says use sequence and list and. Let's look at the and function. This takes a list of bool to bool, a list of bool to bool. Okay, we don't have a list of bool yet because we have to take this character. So what can we do? How can we create a character construct? So we've got this character. Okay. So we get a character out. We can get a character out, and then we've got this list of things to run over it. So I'm going to do it. I'm going to just try and get access to information here. So I'm going to say fmap that, get out the character. And what do we have to return here? Well, we can return anything we want. So I'm going to say we've got our, we're going to use and on, which is going to take a list of booleans. So let's say we have our predicates here. And then I'm going to say on our predicates, run C on them. Okay, where am I making a mistake here? So character, run and on it. That's what I wanted. There we go. Just had parentheses in the wrong way. I had to stare at that for a second. Cool. Okay, so given a, yes, so this will, I think this will actually do something. What will this do? Oh, it creates a parser of a boolean. Okay, it makes a parser of a boolean. Okay. Makes a function of, okay, which is not what we want. I think what this is hinting at, I think this sequence is going to be a little bit of a trick. I think this, I'm remembering something here because I have done this before. It was a while ago, but I did do this. So sequence, I think, is hinting to using an interesting instance of monad. So that'll be good. Okay. So let's look at sequence. So if we have a list of f of a's, then we get back an f of list of a's. I'm gonna have to. I'm getting a bit tricked on this one. I'm gonna have to do the more simple implementation first. Let's start with a really simple implementation. We'll refactor from there. So let's say we take our we parse out a character. Okay, starting off simple. Parse out a character. Now we need to create a parser of a character from this. So that should be pretty straightforward, right? That's just pure C. So this is a parser that will always succeed. But we want to say if well, let's try and run all of our parsers. So let's run all of our parsers. So we've got sorry, all of our predicates. So let's run all of our predicates. So I'm going to say the boolean is running all of our predicates on our C. So we've got this list of character to booleans. So we have to run all of them. That won't compile right. No, it won't. Oh. So our predicates, and then we get our predicate P here. So we say run our predicate with C. And there we go, we've got one hold to do, which is over here. So then we say if that succeeds, then I guess we're saying, what would this be? Hey Aman, how's it going? Okay, sorry, chat is distracting a little bit at the moment. That's fine. Unexpected character parser, is that what we want? Yeah, let's go with that. Unexpected character parser C. Cool. Okay, and we can actually replace this code, I think, with that. So this $sign just means apply, so it's just a way of writing that to that. Want to catch this one? When are you going to be uploading this to YouTube? I'll upload it. It should be up by tomorrow, hopefully. Sorry, sometimes I have to trim it on YouTube. It takes a while to process that, but hopefully tomorrow. Hopefully it'll be up by tomorrow. All right, so I'm going to test this out, and we'll see what happens. We'll see if this is correct. Then we can kind of try and refactor this to the thing the hint that it's giving us. So satisfy all is upper and it's not equal to X. Cool. And then if we do that, satisfy all is upper and not equal to X. Okay, that worked. Now error, we should have an error here. And it is an error because it is equal to X. The first one is an X. True, true. All good. All good. Cool. What do I use to trim the video? I just use YouTube's trimming thing, which I probably shouldn't do, but it's just easy for me to say upload. Twitch is like an export to YouTube button, so I press that and then I go into the YouTube editor and I trim it, and then YouTube spends like an hour or 2 or 3 processing the trims. Okay, so here what we have is running this, so for every predicate we fmap over it and then we run it on our character. So what this is doing is, so we've got a list of characters to boolean. What we do is we chuck in our character here, so then we get back a list of boolean. And then we say and, because remember and, type of and is a list of boolean to boolean, so we just combine all these list of booleans into one value. If that succeeded, then pure C. If it failed, then unexpected character C. Okay, now, we didn't use sequence like I said up here. I said use sequence. And I was trying to do it first up using sequence, and that's kind of the, I guess that's where I kind of got stuck, because I was trying to look at using sequence to begin with. I shouldn't be doing that. I should be doing something else. I should use, instead of using form as bound. Yeah, FFmpeg is a lot faster at doing it. It just copies frames. Yeah, ideally I'd use that, but I don't want to download the video, trim it, and then upload the video. My internet's pretty fast, but I just don't want to go through that effort. It's just easier to do it in YouTube. It is easier. It just takes time for the process to go forward. Okay, I think YouTube actually uses FFmpeg, so it should be quick as well, but for some reason it's not. I'm looking at this and I'm just realizing that there's a couple of things we could do. I think what I've done here is re-implemented a part of satisfy. I think I've re-implemented satisfy. So if I've implemented part of satisfy here, because if I can drop this, I can drop this, and there we go. We're at satisfy. That's a lot easier. There we go. That's a lot easier, and we're still not there. We're still not there because we need to use sequence in some way. What we can do, so notice how the type of sequence, it's a list of FA. It's a list of FA. Need to give back an F of list A. What? We've got a list of character to bool. This is actually an applicative though, that actually satisfies this type. So we can actually say sequence on this. So I'm gonna show this. So we're gonna have a, let's make a list of predicates. Let's make something of this type here, of this type. So is upper, and we'll go equals X. Actually, we'll say not equal to X, because then that makes it actually interesting. whoops, that's what I've screwed up here. There. Why is it not like that? Oh, because I didn't actually screw up that. I screwed up this side. There we go. Cool. Okay, so now we've got a list of character to boolean. A list of character to boolean. Now what we can do is actually say sequence on that. And look at that. Look how awesome that is. So we had a list of character to boolean, and remember that the type of sequence is list of FA to F of list of A. And so we need to find an applicative. So if we look at the applicative, there's a lot of them, but there's this one which is interesting. This is the reader applicative, so it's the one that takes a T to something. So it's something that takes a T to something. So if we look at isUpper, it takes a character to a boolean. And so if we run sequence, we're saying list of character to A will give back a character to a list of boolean of A. So this is sequencing with the reader applicative. So if we had, so look at how we've got this isUpper list of characters to boolean. If we do a sequence on this, we get back a character to a list of boolean, and that means I can just take this, and since it's a function from character to list of boolean, I can just give it whatever we want. So notice how if I put in a lowercase, it's failed the isUpper, but it has satisfied is not X. But if I put it in capital X, it doesn't satisfy that one, but it does satisfy isUpper. So there you go. So if we do a sequence, we do a sequence on our P's, and then we AND them. Whoops. So it's C. We need to do that. There we go. So we take our character, so we sequence our predicates, so then we get back a character to a list of boolean, run that, so we get back a list of boolean, run AND on it, and then we run satisfy on that. Straightforward. Now, HLint's going to tell us what do we want? AND dot sequence P's. Awesome. Cool. HLint's very useful there. And we're all good. That's exactly the same thing. So now we want satisfy any, and I'm going to guess satisfy any is going to be like what we had before, because it says use sequence and or is exactly like and. The type is exactly the same. It just does something slightly different. Instead of doing an and on everything, it'll do an or. So I'm going to guess that's the implementation. Okay. Now I need to do between set by comma. Between set by comma. Okay. So we're going to say we had to begin and P. So between set by comma. So I think is the tip going to say use between char toke. Okay, we can do that. Between char toke, begin, end. Okay, so to do needs to get back a, yep, okay, so cool. So now it says set by and char toke. Set by. Getting closer. So set by needs to have two things. So it needs to have a char. Is that right? I think I flipped this. There we go. I'm just combining together everything I said in the tip there. So it says use between char toke and give it the begin and end there. Then it says use set by, and then it says use char toke. So char toke with comma because it's separated by commas, and so I'm saying set by. So separate P by commas, and yeah, then we got between char toke. But I think we had comma toke, right? we did have Commatoke, and so that's exactly the same thing. So I'm gonna actually just use Commatoke down, Commatoke down now, because it's exactly the same implementation. Cool. We've done everything in MoreParser. Everything in MoreParser. I'm just gonna test it out with these two up here. You can see here, we have that. So it parses basically a JSON list. Basically a JSON list. Whoops, except it doesn't like this bracket there. Well, it doesn't like it at the end here, does it? There we go. Okay, that's fine. But it does like it there. No, it doesn't. Okay. Anyway, that's fine. I'm actually looking at this, I'm thinking maybe I used between and chartoke, yeah, so yep, okay, so me testing out this and looking at this, I revealed a bug, I used is here, I should use chartoke. There we go. That's better. Now we can put, well, we can't put one there, that's fine, but we can put one there. Cool, we're good. Better. Okay, so that's everything in MoreParser. That's just a heap of different combinations that we can use that we built up for what we're going to do now, which is a Json Parser. This is getting interesting. So we're actually going to parse a Json value, and we're going to be fairly close to spec. You might be able to find a couple of different deviations from spec, maybe, but it's, from what I can tell, it's very, very close. So we're going to parse a JSON string, handling double quotes, special characters, hexadecimal characters, going to do everything, right? So this is a JSON string, so a string. So you know, a string has got, it's quoted. So it's like a quoted string. So notice how like it's got the quotes in here, and it also is going to handle like this hex. That's why we did the hex thing in the last module in the MoreParser. We're going to handle hex. What else we're going to handle? And the special characters. Yeah, special characters. Cool. That is the goal. So, tip: use hex from special character between is chartoke to special character. So there's a lot of things we need to do. Like this is pretty involved. This. So hopefully we'll be able to do it in the next hour. I only want to spend like maybe one more hour on this. So hopefully we can do it in an hour. Let's have a go. I'm going to move this tip down the bottom just so we can see it easier. Use hex from special character between is chartoke and to special character. So I'm going to say between, right? Because it needs to be between quote. Okay. This is the first time you're doing these exercises? No, I have done them before. I think I've only done the JSON one once before. I think I've done MoreParser a couple of times though. It's been a while since I've done them though. I have done JSON Parser before. I've done it once before. I think it's only once. So this is going to be pretty involved. Actually, we don't want quote here, do we? Because quote is double quotes or single quotes, which JSON it needs to be double quotes. So I'm going to say is quote. And what I'm going to do here is always trim the end of it. We don't want to trim the beginning of it, right? I was just thinking about that just a second ago because when I was doing quote, I was doing single quotes and double quotes, but we actually want to keep everything after this first quote, and at the end, then we can trim it because it's a JSON string. We can trim it at the end. Even Haskell experts have to spend some time doing these exercises. Yes, you can see me tripping up a bit, even though I've done this before. Yes. Cool. Okay, so now we need to construct a parser that does a JSON character. So I'm actually going to make another function here called Json char. And this is going to be a parser. Actually, I'm going to call it Json String char just to make it obvious what's going on, because there's probably is like I guess there's not a character parser, but I'm going to do this anyway. Json String Json String char. So this is going to be a parser that does everything. It's going to handle the special characters. It's going to do the hex. It's going to do everything. Okay. Oh, we need to make a list of these, right? A list of Json String char. Cool. Okay. Okay. So we need to we've got a list of these characters. So this is going to be interesting, right? So we need to get a character out. I'm going to take out a character. Look, just one character. Because what I need to do, right? I need to say if this character is like a special, like if it's a backslash, I need to say like if it's a backslash, then we need to do one thing. We need to what do we need to do then? This is actually going to be a chars, right? I think that's actually going to be a chars because it's going to be is it going to be a chars? No, it's going to be a char. It's going to be a char. But anyway, we need to parse out one character, see if the character is a backslash. If it is, then read out another one. So we're going to have one character here. So if C1 is a backslash, then we read out another character. And then we need to see if that character is a U. Well, I'm just trying to handle the cases where it's interesting, right? So if it's backslash U, then something. If it's U, then we need to read a hex digit, right? Okay. If it's not U, then it's some sort of special character. So we've got this two special character over here. So I'm going to say if it's not U, then it's some sort of special character. And two special character, it gives back an optional, so I need to convert that into a parser. So I'm actually going to start formatting this because this is getting big. So formatting like this. Okay, something like that. And I need to do something. So if this is an option, so I need to say optional, I need to convert this optional into something. So if it is a special character that isn't in our table, our two special character table, so if it returns back an empty, we need to say, well, that's, you tried to escape something. You tried to escape something that's not a character, so that's not a special character, so unexpected character parser. So we were saying, you put in backslash F or something, and we don't know what that F is. For the full case, we need to say that is just pure. I think that's right. then we want to use whatever the special character thing gives back. So optional is not in scope. Optional is not in scope. It should be. I thought I wrote optional. I thought I just used optional. I did. Where'd optional come from? I don't even know how to make this. There we go. I wrote it intraversable for some reason. For some reason I wrote it intraversable, but I'm going to write it in optional now. I'm going to copy and paste this over in here. There we go. Bugger. Fmap is not found for some reason. Okay. Ignore what I just did there. Just know that I wanted this optional function that we've been using before. It's just fold right before optional instead of list. Okay. Right. Okay, so to special character gives us back a special character. And what do we want? Not the inverse. Right, we want to say from special character. So this will convert it into like an actual JSON, like an actual character. So \t will actually go into a tab. So this is actually like an actual tab because it's a Haskell \t. This is not a JSON \t. So that's an actual tab. So that's good. Okay, so now we've got another hole that we need to do, which is the case that we didn't get a backslash. I think that's all good then, as long as it's not. If C1 is not a backslash, it can be anything else except I don't think it can be a quote, because if it's a quote, we don't want to do that. We don't want to have a quote. We don't want to have quote being a valid character because you have to backslash then quote. So I need to say else if C2 equals a quote. Whoops, I think I can just do a quote. I think that's good. We need to say don't parse quotes as characters. Whoops, C1. Alright, that's a mess. I think it's right though. We parse a character, see if it's a backslash. If it is a backslash, see if it's a U. If it is a U, parse out a hex. Otherwise, if it's not U, if it's not \U, then it's \, some sort of special character. Use that special character. If that fails as well, if it's not a backslash, like if the special character parser fails, then give back a failure. Cool. And then the other case is that if we didn't get a backslash, it was just it was a quote, then that's a problem. We say we're not parsing quotes. Otherwise, neither of those cases, so it's not a backslash and it's not a quote, then we give back a successful value. Okay, this one we probably should run some tests with. So I'm going to parse that one. All good. So that one's got a quote in it and it's still, yes, it's all good. Oh, right, because this is the string, then it had DEF at the end. All good. So \B, that looks like it's valid. ABC, it's valid, cool. So it's looking good so far. Let's go with this one. This one looks like it's more complicated. So 250 ABC, 250 ABC, cool. So it's got some hex digit in there and it's actually parsing that out. Awesome. So I think we're good on that one. It was a little bit difficult, but we got there. Now we're going to do a JSON rational. And it says here, just use this function, read floats. So maybe that'll do. Maybe our read floats function that already exists we'll do what we want. Read floats. Okay, return given a character, give back an optional of a and a character. Okay, so I'm guessing this. So the optional would represent whether it failed or succeeded. The a, so this is a tuple, right? So it's a tuple of a and characters. And this looks similar to our result type. Remember that our parser returns a result, and our result's got characters and a result. So this is very similar. So instead of having result, we've got just a tuple here though. So it'll try and read something from these characters and give us back what it didn't parse and what it did parse. So we should be able to say create a parser that takes in our characters, read floats of that, read float of our characters. Now I'm going to use this optional function that I've written before. So optional takes two things. On an optional, it takes what to replace nil with and what to replace full with. With full, what do we want to do in this case? Convert that into a result. So we've got our, what is it, a and our rest. So that needs to be a result of that, I think, maybe. Let's see if that compiles. It does. Cool. So we just converted that tuple like I was explaining before. Read floats gives back a tuple of a and characters, and so I'm just converting that into a result, like I was saying. It's kind of similar to our result type, but in the case that we've got a b here, I need to say, I guess, unexpected string or something. Unexpected string of C's. I think that's all we can really do. Okay, so I think that'll work. So I can say parse of negative. Unexpected string negative, but if I say -1, -12, so you can see here I've got digits. You can see here I put a .4 at the end there, and that's just the rest of it, so it didn't parse that. So all good. So I think that is a JSON number, so we're getting somewhere. So we've got strings and numbers. Now we need to use string toke to get true. I think that'll just be string toke true, right? I think that's it, string toke true. I'm guessing false will be string toke false. Because we just want to see, like, are these true and false? It's pretty straightforward. Is that actually the string true, and is that actually the string false? And this one will be exactly the same, right? Except null. Parse a JSON array. So now we're getting interesting. Parse a JSON array. What's it say? Use between set by comma and JSON value. So you can see JSON value. It's written just below. It's a parser of JSON value. So we're going to construct up. A JSON value from. So we're going to construct up a list of JSON values. And if you look up above, JSON value is just this. Actually, that's in JSON, isn't it? JSON value.hs. So it's a big data type that represents string, rational, objects, which is just a list of associations here. So you can see here it's a list of strings to other JSON values. Then you got JSON array, true, false, null. So we're going to map everything. Eventually, we're going to map everything into a big JSON value type. But at the moment, what we're going to do is just make a parser that parses in using our JSON value parser. It's going to parse in a list of them. It says use between set by comma and JSON value. I think maybe is that the implementation? I think it. What's the type of between set by comma again? Oh, you have to give it a beginning and end, right? So we have to say beginning is that, and end is that, and then we say JSON value. Awesome. I think that is actually the implementation. Okay, now parse the JSON object. Use JSON string char toke between set by comma and JSON value. Okay, so between set by comma, we want to use separate. We want to between these two things, right? We want to between these braces. Then we need to create a list of associations, right? So I'm going to say JSON object assoc. So this is similar to what I did before. Just make my own function here. Hang on, this one is a parser of assoc. Oh, but I just want one assoc, right? Yeah, I just want these. Yep, okay. So I want to have something that parses out the string, so the key, colon, value. That's what I want as well. I don't want the list, because this is already going to do the list part for me, isn't it? So I'm just going to put a hole in there and see if this is the only error. It is. Cool, so I just have to implement this. So it is going to parse a Json String. Then it's going to parse our char token of colon. And then it's going to parse the Json value. Cool. And so you can see the hole here. So this is the function I have to supply. So to combine these three parsers, so I've got this Json String parser. So this is the key. This is the colon in between, and then that's a Json value. So that's the value. So you've got the key, colon, value. I'm not going to use this colon though, but I need to combine these three values in some way. So I need to combine the key, the colon, and the value in some way. So I'm going to say I need this key, don't need the colon, do need the value, and then I'm just going to make a tuple out of that because it needs. You can see the return type up here is character, comma, Json value. So we need to construct a tuple. So combining these three values, I'm going to make a tuple that ignores the middle value. So it ignores that colon. We don't care that we care that there's a colon there. We don't care what the colon is. We know that it's a colon, so it doesn't really matter. Okay. So that's JSON object is assoc, and it's used in this way, just saying that between these two braces, we need to have a heap of these associations separated by commas. Awesome. Now we're down to the last kind of like real tricky part, which is the JSON value. So now we need to combine all of these things. So notice how it says here, tip is use everything. Use spaces, JSON null, JSON true, JSON false, JSON array, JSON string, JSON object, and JSON number. Combine them all up to make a JSON value. And the reason why I think it says spaces is that it wants to ignore spaces at the beginning. I think that's what it's saying. So I'm going to say ignoring the spaces at the beginning. So I'm going to use this right apply thing. Actually, no, I want to use a left apply, don't I? I'll say left apply. No, hang on. I'm getting myself confused. Which one's which? Yes, I want right apply, don't I? Yes, cool. Okay, so using spaces, but ignoring them. So let's start off with this. This should work, right? No, it won't. What I need to do is map this JSON null into. So if you look at the type of JSON null, it gives back a parser of characters. But I need to give back a parser of JSON value. I need to give back a JSON value, and I've got this JSON null here, so I need to map this JSON null. So the result of this, I actually don't care about what characters that are in this thing. I only care that it did parse a null. So what's this right apply? So right apply, if we look at right apply, takes given an applicative f. So if you're giving me a value of fa and a value of fb, I'll give you back an value of fb. And this is more interesting than just flip const. It's not just going to get back this fb. It's going to use this fa, but it's only going to use like the f part of it. So it's only going to use the applicative. People call it effect, or it uses the applicative instance to come up with this new fb. So it combines everything. It just doesn't combine. It just doesn't use this a. So if you had like an optional, in the case that let's say this applicative f, let's say this f is optional. So we'd have an optional a, then we'd have an optional b, and we're going to get back an optional b. When it uses the applicative, it's going to make sure that the optionals are both full. So if you give me an empty and then a full, I'll give you back an empty. Or if you give me, if you give me two fulls, if you give me a full of A and a full of B, I'll give you back the full of B. So it's just it's a way of using these two things. And in the parser case, in this case that we're doing, it's going to parse the A, then it's going to parse the B, and it will return the value of parsing the B, but it's actually going to parse both. So it'll consume the input from both and make sure that A doesn't fail, the first one doesn't fail. If the first one fails, then it's going to fail the output. But it's going to combine them together. So this write apply just says, make sure that the first thing parsed properly and it didn't error, and then give me back the result of parsing the second thing. So in this case, it's going to say, parse out the spaces. So consume all the spaces from the input. I actually don't care about the spaces being there. I just care about this thing. So it's just a way of saying, parse the spaces off. I don't care about the rest. Cool. It is lift A to const ID, if that helps. Yeah, so if you know what lift A does, it's pretty straightforward as this thing here. So const ID or flip const, same thing. Okay, so in functor, we saw this other useful function. So there's similar function to that write apply. There's also this left map, or this here is called anonymous map. So what we want to do here is, because we don't care, similarly to what we had before, where we don't care about the spaces, we just care whether spaces are there, we want to get rid of them. With this JSON null, we only care that JSON null was there. We don't actually care that it says null the string. We don't care about that. That's what the parser does. It ensures that. So we don't care about the string that gets returned from this. So we can say left map. And if we reload that, there we go. So now we have this thing called Json Value, and it will be able to parse null. So if I give it null here, you can see here it goes back null. So I've got a Json Value parser that only returns, that only works with null at the moment. Okay, so first step was null. Let's put in true. So Json true. So these are all very similar because these are all basically the same, right? There we go. So now we've got a parser that does null and it does true. Next step is obviously false, so let's do that. So notice how this is all very similar. We're taking in this thing, we're ignoring that it says false the string. We don't care what the string is from this parser. We just care that it did parse, and so we're mapping that to a JSON false. So we're just mapping it to the appropriate JSON value at the moment. So we've got true, false, null. So we've got that much. What else do we need to use? So we've done. Then we've got the spaces: JSON null, JSON true, JSON false. Now we want to do a JSON array. JSON array. We need to construct a JSON array. How do we construct a JSON array? We'll get a list of JSON value. I think if we look above, we have that with our JSON array. Yes. So in this case, we actually do want to use use the result of this parser. So JSON array, we'll just map it into a JSON array. Is that right? It doesn't like that. Oh, because I need to put or in there. There we go. So that's constructing a JSON array, so we've done that. We need to do a JSON string. JSON string, I think this one we do care about what gets parsed out again, so JSON string. JSON object. And JSON number is the last one. So notice how we're just kind of taking these low-level parsers and we're mapping them into the data type that we need. JSON number is a problem. Well, it needs to be JSON rational. There we go. So now we've got a JSON value parser. So if we run this, I think we've got spaces in the right place. So we already tested out true. Let's try parse like a complicated JSON object. There we go. So I parsed it out, it made sure it's got the braces, it's got the key here, JSON true, so that maps to true. Key here goes to 7 and then false. Awesome. And we should be able to put spaces at the beginning. Oh, didn't like that. Why didn't like that? Oh, because I said parse JSON object. That's what this said here, but that's not what we want. We want JSON value, don't we? There we go. That's better. That's better. Cool. So I think that's actually an error in the, that might be a little bit of a mistake in the, oh, maybe not actually, because it's, yeah, okay, no, that's fine. But yeah, real good. Cool. So it's pretty straightforward. Consume some spaces, run the first action, then consume the next thing, and return that, ignore the spaces. Yep. Okay, so that's our JSON parser. It parses in any JSON string. Now there's one last function that we need to implement before I finish, which is read a file into a JSON value. So we've got this read file in IO. So we've got read file. So given a file name, read the file. And then we're going to run, we're going to parse it. So we're going to use our monad to get out, what's this going to give us? The content. And we're going to parse JSON value with the content. Whoops, actually we want to map it, don't we? We don't want to use the monad, we want to map it. There we go. And we can even drop this this C like HLint is telling us. So there you go, now we can say read JSON value and give it some sort of JSON value. Do we have any JSON values in here? Okay, well, whatever this is, this looks like some CI thing that's in the FP course, so let's read this. So what is it? Job sets CI/jobsets.json. There you go. Look how awesome that is. It's reading in this JSON file that's just coincidentally, I think, in the repository, because it's got CI information in it. But it's reading it in from the file system and converting it into a data structure. So this is a data structure we can actually work with, which is super, super cool. So this is a JSON object. We can pattern match on this, or we can get out all the keys. We can do whatever we want with this, since this is now just a data structure in our memory. And we constructed this from scratch, just from strings. We were able to implement this. Super cool. Strings and functions, that's all you need. Awesome. Any questions about JSON? We've finished the module. We can mark them off. MoreParser and JsonParser, done. I'm happy with that. Anyone want to send through some tricky JSON that we can test out? What we should have in the repository is something that actually like exhaustively, well, maybe not exhaustively, but I don't know, does some pretty good testing of this. That'd be really good. I think there's some tests underneath. Here we go, JSON Parser test. Here we go. This got a little bit, yeah, it could be a little bit more detailed. Like, there could be something in there that gets pretty, do Reddit's JSON. What does that look like? Here we go, old.reddit.com/.json. All right, give that a go. Whoops. Oh no, what happened there? Unexpected character, it doesn't like that one. Oh, whoops. That'd be why. I screwed up the, is it dash capital O? There we go, there we go. Cool, let's give this a go then. It's taking a while, it's not the quickest parser. Although some of this will actually be probably like trying to pretty print it. Well, not pretty print it, but trying to print it at all. There we go, it parsed. It parsed. That's how good our JSON parser is, written from scratch. This FP course is super impressive. It builds up a JSON parser from scratch. Super, super impressive. this works. Like it's a very big JSON file. How big is this? Okay, 116K, we can parse it. We've written a parser from scratch using just functions. Super cool. Functions and strings. Cool, so I am going to commit this. Let me know if there's any questions. Let me know what we want to do next time. So I'm going to upload this to YouTube. Hopefully it'll be up there in the next day. Let me know if there's anything more in the course we want to do. So what we haven't done is, we'll list zipper. I don't really want to do that. I'm not very interested in that. Extending co-monitor we haven't done. We can talk about those. Interactive, anagram, fast anagrams, check. We could do those. Those get a little bit more interesting, I guess, in terms of data structures. But we're getting through FP course, but there's not a huge amount left. So let me know what you want to see next time. Next week I won't be streaming. I'm actually moving to India for a while, so I won't be streaming next week, and I don't even know. I think the time will have to change a little bit because India's time zone's a bit different, and I don't know when I'll have equipment and that ready in India, so we'll see. Sorry if I'm not streaming for a little while. I will be busy moving. Okay, yeah, thank you. So I'll upload this to YouTube after we find someone to host. Twitch just keeps changing and it's annoying. You used to be able to find functional programming people pretty quickly. If there weren't never really many people, but here we go. Deprogramming. That's probably more interesting than most. You released the Queensland Functional Programming Lab released a JSON library last week, and it's called Wargonaut. Have a look at this. Flexible, precise, efficient JSON encoding and decoding library. There we go. So if you, instead of writing your own JSON decoder, or your Json Parser, instead of writing your own Json Parser, you could use this. That's cool. I think knowing Queensland Functional Programming Lab, one of the motivations would be to not have type classes, and you can see here, yeah, there we go. Int, text, bool. Yes, that's good. That's good. Awesome. I haven't actually looked much at this, but I'll have a look at it some more. Cool. So I think we're going to go to the deprogrammer. Unless there's someone more. No, C++ and Python. We're not going there. We're going to the deprogramming. So thanks for coming in, everyone. I'll upload this to YouTube, and let me know what you want to see next time. It might be a little while before I get around to being able to stream again, but yeah, let me know. All right, we're gonna raid Wild Noob, and make sure to subscribe on YouTube if you want to get notifications when the video comes out. All right, say hi to Wild Noob for me.